Seeing as it's 4:10, I'd like to go ahead and introduce our colloquium speaker for today. It's my great pleasure to introduce Jennifer Kay. Jen is an associate professor at the University of Colorado Boulder in the Atmospheric and Ocean Sciences Department, and a fellow of the CERES, the Cooperative Institute for Research in Environmental Sciences. Jen has been at Boulder since 2014, following a postdoc at UCAR, at NCAR, the National Center for Atmospheric Research, and before that, a PhD at the University of Washington in their Department of Atmospheric Sciences. Jen is a specialist in the interactions of clouds and polar processes within the climate system. And one of the things that I really like about her and about her work is that she crosses the boundaries between observational science and modeling science, and actually resists being labeled as an observationalist or a modeler. And I think that really shows through her work, which really synthesizes our best knowledge of satellite observations of cloud processes and their behavior in climate models, and how those relate to evolution of sea ice and ocean atmosphere responses to climate forcings. She's a recipient of the Henry Houghton Early Career Award from the American Geophysical Union in 2017, and also was the Turco Lecturer on Future Horizons in Climate Science at the American Geophysical Union in 2019. So she's running a great research program, mentoring all sorts of great students and postdocs, and has been thinking also about the implications of climate change and polar climate change for human and ecosystems as well. So is quite a broad thinker. So I'm really looking forward to your talk today, Jen, on how clouds affect global warming. And please go ahead, and I'll keep my camera off. And just a note about questions. So we'll have questions in the Q&A, and we'll be taking a look, but we'll postpone sort of the full set of questions for after Jen's talk. Thanks.
Great, thanks so much, Paul, and for the invitation. Today I'm going to talk to you very generally about how clouds affect global warming. And as promised in the abstract, I'll start with really not much of an assumption at all about your understanding of clouds and global warming, and really try to motivate this from the ground up. But by the end of the talk, I hope you'll see some of the work that's going on right now, and how we're really making progress on this very complicated topic. So obviously the climate is changing due in large part to increases in greenhouse gases. So here we just have a couple of the canonical observational data sets that show us evidence of this change, in particular the increases in atmospheric carbon dioxide concentrations measured in Hawaii. So this is the Keeling curve. You know, we're now over 410 parts per million. It's really hard to believe. And then when we look at the surface warming, we see basically large warming in the Arctic, especially over the last couple of decades, but the globe steadily increasing as well. And the Arctic is definitely a place where we've seen a lot of fundamental changes to just the basics of how the system is operating. So here, observed Arctic sea ice loss. In fact, this last summer, 2020, was the second lowest Arctic sea ice extent on record. 2012 is the current record holder. But in fact, if you look at the last 14 years, they are the 14 lowest of the satellite record, which goes back to 1979. And this is a really, of course, big change to the Arctic system, with impacts, you know, on ecosystems, on transportation, on people who live in the Arctic, but also has the potential to influence something like the cloud cover in the Arctic. You think if you're going to change a surface and over the ocean from being covered with ice to one where you have open water, there's a new potential for moisture from the surface to enter the lower atmosphere in particular and protect and change the clouds. And so this is an example of a cloud feedback in the system where, you know, we're increasing CO2 that's causing warming and sea ice loss, and then how the clouds change in response to the sea ice change could either amplify or dampen that warming. And so we'll talk a little bit about cloud feedbacks, but I just want to motivate them very basically from sort of the first principle observations of climate change. So this topic is really big. How do clouds affect global and Arctic warming? And so I'll do my best to kind of summarize where I think we are, relying on some recent synthesis reports, and also covering some recent research that I've done and others have done that I think is important for these questions. I'll rely in particular on the Intergovernmental Panel on Climate Change fifth assessment. So this was an assessment that was put together in 2013. It was published, and it was the first time actually in these kind of large assessments of the scientific evidence for climate change commissioned by the governments of the world, where there was an entire chapter dedicated to clouds and aerosols. And this was in recognition of the processes that control clouds and aerosols being really important for understanding climate and climate change. And there's another version of this an updated version of this kind of scientific assessment that's in progress now, AR6. And I'm sure there will be a lot more discussion of clouds and aerosols and precipitation in it. We've definitely made progress since this last assessment, but there is much progress left to be made. So in this assessment, I like this because it's trying to motivate things from the ground up. And this is one of the ways that I also think about why clouds might be important for the climate change problem. And that is to just look at how clouds affect the mean climate. And so we can do that by looking at something that's called the cloud radiative effect. So this is just asking would be the top of atmosphere energy budget with and without cloud cover. And what we can see here is that the net effect of clouds on the climate system is a reduction in the top of atmosphere energy budget. This suggests that clouds globally are cooling the system, and it's a big number, minus 21.1 watts per meter squared. For some point of reference, when you double the carbon dioxide concentrations in the atmosphere, which is, bigger forcing than we've seen so far from our changes in CO2, that's about 3.7 watts per meter squared. So the clouds are having a radiative influence on the system in the mean state that's very large, and you could imagine could change and be of appreciable magnitude when compared to radiative forcing. Clouds, of course, have different effects on the climate system, whether you're thinking about shortwave or longwave radiation. And we can think of this as the shortwave radiation being basically sunlight being blocked from the surface and reflected back to space. And so that cools the system. But clouds also have a long wave effect on the system. Just like greenhouse gases in the atmosphere, clouds absorb and re-emit long wave radiation, and that actually causes the surface and the atmosphere to be warm. The shortwave effect of clouds dominates over the long wave effect of clouds, which is how you end up with this kind of global cloud cooling. But of course, this balance very much depends on the local situation that you find yourself in. So for example, if you're in the Arctic in the middle of winter where there's no sunlight, the effect of clouds on the climate system is entirely in the long wave and acts to warm the Arctic surface. So these large numbers in terms of watts per meter squared are really what makes us really think clouds, if they did change, could really be an important element of how the climate system is going to respond to an increase in greenhouse gases. So I know not all of you think about these processes, so I thought I would motivate this and how we try to quantify these things by giving you a brief primer and feedbacks. So basically what we're doing with this system is when we increase greenhouse gases or change other forcings, is we're implying a change in the forcing at the top of the atmosphere, which can be measured in the units of watts per meter squared. In equilibrium, there is this net balance at the top of the atmosphere of 0 watts per meter squared. So once we impose this forcing, how do we get back to an equilibrium of 0? Well, we get back to that equilibrium in the case of increasing greenhouse gases by surface warming. And that surface warming here is measured in degrees Kelvin. And so then you can think, in order to get the units right here, basically we have to multiply that surface warming by a feedback parameter. And that's going to have the units of watts per meter squared per Kelvin. And so it's the top of atmosphere flux change per degree surface air temperature warming. And you can see that these, in this particular equation, this feedback parameter has been partitioned into different types of feedbacks. And these feedbacks could include, for example, the Planck feedback or the water vapor feedback, the albedo feedback, and here, lastly, the cloud feedback. And so these feedbacks are really important to understand. Overall, this feedback parameter is negative. That's what enables us to get back to some sort of equilibrium state. But individual terms in this, for example, the water vapor feedback, the surface albedo feedback, we know those are positive feedbacks. And so they act to actually make this feedback parameter in sum less negative. So the question we'll really think about here is, what is this feedback associated with clouds? And how does it compare in magnitude and uncertainty to some of these other climate feedbacks? So there's a very nice paper by Mark Zelinka and Dennis Hartman that kind of reviews kind of the state-of-the-art climate model simulations from this 2013 climate assessment report, and plots the mean feedbacks in that generation of climate models, which is called CMIP5. And so here we have, let's start here on the lower right, we have the net feedback, which we said, globally would have to be negative in order to, basically get us back to some sort of equilibrium. And it is indeed negative, the net feedback. But we can see other feedbacks that are partitioned here are not negative. So for example, we have the water vapor feedback. When you get more water vapor in the atmosphere in a warmer climate, that warmer, wetter atmosphere is more emissive, and that leads to a positive water vapor feedback. We can also think about the surface albedo feedback, where in the high latitudes, when we lose the sea ice, we end up with a darker ocean surface, and that ends up being a positive feedback on the system because the darker surface starts to absorb more shortwave radiation, further enhancing the warming. We can see the big negative feedback in the system is actually the temperature feedback. So this is just from Planck's equation, and it's really important for sort of stabilizing our climate. And then the cloud feedback, which we will talk about in detail in this particular talk. So here it is, the average climate model global cloud feedback. And you can see globally it's positive, but there's certainly regions where it is negative. In particular, we see this strong gradient in the high southern latitudes going from a positive feedback to a negative feedback. And this particular map is really nice because it helps us think about the different cloud regimes and the different cloud environments that exist on the planet and how clouds might change in them in the context of climate change. So even though this paper plots the average cloud feedback, it's important to note that the cloud feedbacks in climate models are uncertain. And in fact, if we look at the feedbacks here, again, just in the global mean sense, we'll look at, for example, water vapor and the lapse rate feedback. The confidence as assessed in this assessment report is that we have a high level of understanding of how those will change. And you can see that expressed by pretty small intramodal spread in the feedback. Whereas for the clouds, sure, the mean feedback is positive 0.6, but the range is much larger, from minus 0.2, a negative feedback, to 2, a much more positive feedback. And the confidence level here is only medium. Now, aerosols, which I won't talk much about in this talk, but I think merit being mentioned, as the last assessment really tried to look at aerosol processes. And even though there's pretty low level of understanding, it seems like actually the absolute magnitude of the aerosol feedback is relatively small. So it's really the clouds that are uncertain here. And so that's what we'll really focus our energy on. And in this last assessment report, the IPCC AR5, the global mean cloud feedback is assessed as being likely positive. But there's a lot of discussion in this chapter, and there's been a lot of discussion in the scientific literature about all the different ways that clouds can respond to a warming climate. And it's this myriad of processes that really make it quite complicated to assess and really know what the global cloud feedback is, and also what it is in the models and whether or not we trust it. So if we look, and again, another figure from this assessment report, just showing from equator to pole, the different types of environments we tend to find clouds in. So on the equator, we have these very deep cumulus clouds and anvil clouds. We have, as we move to the mid-latitudes, we have basically lower cloud top heights, a lot of mid-latitude storms and other dynamics. And so those kinds of dynamics start to become important here. For example, the poleward shift of storm tracks. And then as we move into the polar regions, this hint of more polar clouds. So this cartoon is really trying to represent the number of processes that could be relevant and influence cloud feedbacks. And one of the things that's emphasized in the report is that we have relatively high confidence and high clouds, and relatively low confidence and low clouds. And it turns out these low cloud climate feedbacks end up being an area of really intense and important research right now. So why was the global cloud feedback assessed to be likely positive? So in the sense of enhancing greenhouse warming, there's kind of three main cloud regimes that are implicated here. The first is the rising of high clouds, but even as they rise in the atmosphere, they are maintaining a fixed anvil temperature. So they're not actually emitting any more radiation back to space. And that results in a positive feedback. There's also reductions in subtropical low clouds, and these subtropical low clouds really dominate in the shortwave radiation. And by having fewer of them, you end up with less shortwave cooling of the clouds. But the mechanisms underlying this reduction in low clouds are more uncertain, and we'll talk about that a little bit here. And then finally, more polar clouds as a result of reduced sea ice cover. It turns out this increase in polar clouds is something that's operating mostly in the polar night and during times of the year when long wave radiation is dominating. So we're going to get more long wave warming from polar clouds. So I'm going to go through these three different regimes and just introduce some of the studies behind them and why we think that these cloud feedbacks might be positive. So here, a robust prediction for tropical high clouds having a positive long wave feedback. So here we have the net cloud feedback. This is what we were looking at before. And now it's been partitioned into the long wave cloud feedback and the short wave cloud feedback. And you can see that while there are differences in both the shortwave and the long wave cloud feedback in the tropics, that the long wave cloud feedback is what's dominating this tropical deep convection response. So why is this long wave high cloud feedback positive? What is this fixed anvil temperature or FAT hypothesis? The idea here is that basically as the climate warms, isotherms move up in the atmosphere and convection deepens and goes into higher parts of the atmosphere, but that the cloud top temperature itself remains constant. When the cloud top temperatures do not warm in step with the surface warming, basically the tropics becomes less efficient at radiating away heat. And as a consequence, we have a positive feedback on the climate system. And we can see evidence for this type of behavior, not only in large scale global climate models, but also in more realistic and high resolution, but also more idealized simulations. So here, this is just some simulations. These are performed at 1 kilometer, so much higher spatial resolution, something that's convection permitting. And basically, we're looking at some idealized simulations where we've just increased the surface temperature and looked to see what happens to the cloud fraction and the cloud temperature. And what you can see is that the clouds are moving up in the atmosphere, but the temperature at which they're radiating back to space is actually staying the same. So through these kind of idealized and high resolution cloud simulations, and also sort of large scale numerical models, we see evidence for this positive long wave cloud feedback. What about the low cloud feedback? So we talked about this, that in the subtropics, the low cloud amount decreases, and that leads to less shortwave or solar cooling. And it was assessed that this lacks a well accepted theoretical basis. And the complexity of these low clouds is definitely important. While in the subtropics, much of the cloud cover here is dominated by processes that only involve the liquid phase, there's a lot of complexity and interaction with the precipitation, with the diurnal cycle, with the sea surface, with entrainment into the free troposphere. And there's a nice review paper by Brotherton in 2015 that reviews some of the different ways that a warming climate, in a particular warming climate caused by increases in carbon dioxide, might change these clouds, low clouds over the ocean, so the marine boundary layer stratocumulus. And it's no surprise that given this myriad of different processes and competing processes, that we don't have sort of a consensus for the main mechanisms that would cause these clouds to decrease. Although we do see in more and more simulations that try to represent the balance of all of these different mechanisms, that the clouds tend to decrease. Okay, finally moving to the Arctic, where I mentioned that there's evidence for low clouds increasing in the dark months of the year, leading to a positive long wave cloud feedback. And this is work actually that I've done, looking at the observational evidence for a seasonally varying cloud response to Arctic sea ice loss. So what we see is actually in the summer, there's a lot of liquid clouds in the Arctic, and the Arctic is a cloudy place, don't get me wrong, but the clouds in the Arctic are not responding to reductions in summer sea ice cover. And that suggests, based on the observations, that there's no cloud sea ice feedback. In contrast, if we look in the non-summer seasons, again, when long wave radiation will dominate, we see more low clouds, often liquid containing clouds, over open water than over sea ice. And this provides evidence for long wave non-summer cloud sea ice feedback. And the reason for this kind of seasonal contrast and how the clouds are responding to the surface is actually seen somewhat visually through this picture looking down from a satellite. This is Barrow, Alaska, and this is the Arctic coast and the Arctic Ocean. And what we see are these roll clouds, which are evidence of strong air-sea coupling. And this makes a lot of sense. When we go into the fall, the atmosphere is rapidly cooling. The ocean underneath, especially if it doesn't have sea ice, has been warming, baking in the sun over the summer. And this provides the perfect recipe for coupling or shallow convection in the Arctic. In contrast, in the summer, the atmosphere is pretty warm compared to the underlying ocean, which has a lot larger heat capacity, and it's much harder to change its temperature. So even though it's not super stable, it's stable enough that you don't end up with a lot of air-sea coupling, and you visually don't see a lot of these kind of roll clouds, which are sort of visual evidence of this coupling. So in addition to visual evidence, we've also worked with data from spaceborne LiDAR and basically tried to look in these regions of the Arctic where there's sea ice cover in some years and not in other years at a really high spatiotemporal frequency. And what we see is actually the profiles of clouds over open water and sea ice are very similar in the summer, again, suggestive of this lack of a cloud sea ice feedback in the summer. But if we look in the fall, we can see increases in the low-level cloud cover over open water as compared to over sea ice. Again, suggestive of more low clouds in response to Arctic sea ice loss. So we've talked about these three very different regimes, very different places where we could have evidence for a positive cloud feedback. What about negative cloud feedbacks? And in particular, one of the more striking things, which I mentioned, was this negative cloud feedback at the mid to high latitudes, especially in the southern hemisphere. And this feedback in part occurs because clouds change phase in a warming climate. At least that's what's happening in many of the climate model simulations. So here, for example, if we look at a zonal mean from 30 degrees south to 70 degrees south, and we look at the feedback due to clouds, we can see this positive feedback, maybe around 40 degrees, and then transitioning, and we get, poleward of 50 degrees south to become a negative cloud feedback. And so this negative cloud feedback is important to understand. We don't have all that many negative cloud feedbacks on the planet. So it's kind of interesting to think about what the processes are. And it's also quite complicated to diagnose. And that is because there's also other feedbacks that are very large and having influences on the energy budget at these latitudes. So here, for example, we're using a novel method to separate the feedback due to sea ice and the feedback due to clouds. And so I just want to keep in mind that methodologically, this is not so easy to separate these different feedback processes. So one of the issues that has been noted is that while there are these very large negative feedbacks at high southern latitudes, there's also some very large biases in many of the models at these latitudes. And in particular, there's a real bias in the present day simulation of cloud phase. So if we look, the present day ice cloud is overestimated in many models. And this is just one example from CAM5, which is an atmospheric model that's part of an Earth system model. And we can see that compared to observations, there's a lot more ice cloud than there are in observations. And maybe hints also that there's insufficient liquid clouds. So if these transitions between the phase from ice to liquid in a warming climate are what's driving these negative cloud feedbacks at these latitudes, I think we have some cause to be concerned about models that have large biases in their mean state, because basically they will start out with too much ice to melt, which could end up giving us a negative feedback that's not all that realistic. So that is indeed the case. And I don't know if you all read the press. This was coming out about a year ago when the first versions of the next generation climate models were coming out, and they were all showing more warming in response to increases in greenhouse gases. And it led to stories like this that even appeared in the popular press. Climate models are running red hot and scientists don't know why. I think this is a very provocative title, and I think there's elements of this that are true. There's certainly a lot of reasons we don't know why, but there's also reasons that have been diagnosed, and I think we know a lot more than we did a year ago. And in particular, we know that one of the feedbacks that was perhaps leading to less warming in the last generation of models is now leading to more warming in this generation of models. And that is this negative optics feedback. So for a fixed cloud condensate amount, liquid is more reflected than cloud ice. And as we've seen, present day ice is often overestimated in models. And so the implication is that the last generation of models should have warmed more than they did. And in fact, we are seeing evidence that the next generation of models, the ones we're looking at now, the ones that are running hot, are warming more than the last generation due to this negative cloud feedback. And I won't talk about this in detail because I understand you have Mark Zelinka coming to give your colloquium next week, and I'm sure he will talk about this. This is work that he's led, looking at the reasons for why the current generation of models is warming more than the last generation. But in particular, some of these changes in the mean state, in some cases to make the mean state more realistic by adding more liquid instead of too much ice, these are actually something that is actually pushing the models closer to observations. So definitely a lot of questions around this particular topic. So in addition to this optics feedback, there's another feedback, and I think I'll talk about this just to illustrate how complex some of these questions really are. So again, talking about a phase feedback going from ice to liquid, there's another negative feedback that could come in, and that relates to precipitation. So warm precipitation, i.e. precipitation that's forming only from the liquid phase, is actually not as efficient as cold precipitation. So ice that's precipitating, that's initiated by ice phase processes. And as a consequence, warm clouds actually are able to persist longer or have lower precipitation efficiency than cold clouds. And so I think this is another example of a feedback that's important with cloud phases and its phase changes. And it's really one that maybe has received less attention. The representation of precipitation processes and climate models is something that's being improved, and in particular, their coupling to clouds is more sophisticated than it was in the last generation of models. So I think there's a lot of questions here and a lot of work to be done to look at these cloud phase feedbacks. And this is work that's ongoing right now, and I think is an example of the type of research that really shows that, scientists aren't completely certain about what clouds and precipitation are going to do in the future. And we don't entirely trust climate models. And it's not as simple maybe as just the cloud optics feedback that's been discussed in the literature. There may be also changes from cloud lifetime. So this is work from a paper that's in preparation, and I think in the interest of time, I'll just keep moving through, but if you have questions about this, I'd be happy to talk about it. So just a summary that there's a lot of feedbacks that could happen associated with phase changes from ice to liquid in clouds under global warming. Two of them that have received attention recently and I think really cause a lot of uncertainty in how much warming we see in global climate model simulations. One is this negative optics feedback, and the other is a negative lifetime feedback. And there's hints that, one of them may be overestimated while the other is underestimated. And so I think there's a lot of work left to do to really understand how phase changes are really going to influence cloud and precipitation processes and radiation under global warming. So coming back to this quote, I think there's a lot of truth to this still. There's a lot of interesting science left to do. Okay, so with the last little bit of the talk, I'm going to kind of change directions a little bit and talk about a paper that we actually published this past summer. And I think this will be fun for you guys to see because it's an example of how we can use global climate models to try to assess what the cloud radiative feedbacks are in them and do so in a way that's really direct. So a lot of the feedbacks that we've looked at so far have been assessed using indirect methods after the fact. Here, we're actually going to go into the guts of a climate model. We're going to disable the cloud radiative feedbacks in a process called cloud locking. And we're going to ask, what does that do to the amount of surface warming in the climate system? So yeah, the research question here is really, really general. What is the influence of cloud radiative feedbacks on surface-based warming in a modern Earth system model? And what's kind of new and novel here is that we're really going to disable cloud radiative feedbacks. We're going to make the clouds just be a constant value that varies seasonally and spatially and at every time step, but doesn't actually change as the climate system warms. And we're going to do that both regionally and globally. So we're going to look at 3 pairs of simulations. And in each pair, we'll have a control and a 2 times CO2 simulation. And then we'll also have simulations where the clouds are active. So that's what's specified here by CNT. We're going to disable the cloud feedbacks globally, so at all locations on the globe. So that'll be this GCL simulations. And then we're going to disable feedbacks only in the Arctic, so only from 70 to 90 north. And this will help us address questions like, what is the influence of Arctic cloud blocking, Arctic cloud radiative feedbacks in isolation on Arctic warming versus how much global cloud feedbacks, so feedbacks that are happening at other latitudes, how do those influence Arctic warming? So let's jump right into the results. So the first result, we're just going to look at the zonal mean response again to this carbon dioxide doubling. And here we're just going to compare the simulations where all of the clouds are active. So that's the control. With the simulation where all of the cloud feedbacks are disabled. So that's the global cloud block. And what we find is actually that these global cloud feedbacks, they actually increase global and Arctic warming both by about 25%. So here's hints that in this Earth system model, the cloud feedback is a positive feedback. It's acting to increase the amount of warming. And also that the global cloud feedbacks are important in the Arctic for increasing warming. So now we're going to look at these same type of plots, but we're going to add the simulations where we've disabled the Arctic only cloud feedbacks. So here we have now in blue the Arctic cloud block simulations. And what's really fascinating here is, especially if we look at both the warming and the amplification, that this disabling the Arctic cloud feedbacks is really having a negligible influence, both on the Arctic climate and on the global surface warming. So this really suggests that in these global cloud block simulations, the reason that we're getting more warming in them is not because of changes in the Arctic clouds, but because of changes in the non-Arctic clouds and in the cloud radiative feedbacks not in the Arctic. We also looked at the seasonality of Arctic surface greenhouse warming and amplification, and we find that cloud blocking, while it is changing the amount of warming, especially this global cloud blocking simulation, we are seeing that the same seasonal fingerprints of Arctic surface warming and Arctic amplification are present. So namely, we have the least amount of warming in the summer and more warming as we move into the fall and Arctic winter. And so clouds are not sort of changing the sort of canonical structure of Arctic warming. So some may find this result kind of surprising. There's a lot of discussion about Arctic clouds and if they're important for the climate system. And this is just one model simulation, one model experiment, but I think it's a really convincing experimental design. And so one question you should ask is, is this model sort of fit for the task of asking, what are the global cloud radiative feedbacks and the Arctic radiative feedbacks? And this is a whole discussion we could have for a long time. I do want to say that this is a pretty well-vetted and state-of-the-art Earth system model. So if we look at sort of generic comparisons amongst all of the different models of this class, this model is, one of the best performers in terms of, for example, normalized distance from observations for temperature and precipitation. It also does a decent job in the Arctic, where, for example, it can reproduce the recent observed Arctic sea ice loss. It also reproduces this seasonal cloud response to Arctic sea ice loss that we talked about that was in the observations. So there's a lot of reasons to understand that this model is providing some useful information about the influence of Arctic clouds on the surface. But there's one thing that is really important for interpreting these results, and that is that this model tends to underestimate the supercooled cloud liquid at the high latitudes. And this is really important because liquid at the high latitudes is very important for how Arctic clouds interact with radiation. And so there's a hint here maybe that the influence of the Arctic cloud feedbacks may be underestimated. So methodologically, I think this is a really convincing way to go, but we still need to understand the model's mean state and compare it to observations in order to have some assessment of how much we really trust the feedbacks that are represented in it. So I'll just provide a summary of the results from this study. So we find that the global cloud radiative feedbacks, they increase global and Arctic surface greenhouse warming. We're finding in contrast that the Arctic cloud radiative feedbacks are having a pretty small influence. And there's some concern about the mean state of the model, which I think merits redoing these types of experiments where we can really actively diagnose the influence of cloud radiative feedbacks on the system in the future. And more broadly, I think this work really demonstrates the value of disabling feedbacks in a well-characterized Earth system model. So I'm going to leave you there. I hope this was a nice introduction to this kind of very general question: how do clouds affect global and Arctic warming? I've put my email address here. I'm happy to take questions now or over email. And I hope I've made you excited to think about some of the big questions that remain in terms of understanding the amount of warming that we might get into the future as a response to greenhouse gas increases, and the important role that clouds in the many myriad of environments that they exist in play in that warming. So thank you very much.